Hey, we're going to look at continued kinetics, topic 5.4, elementary steps. Okay, I'll probably go ahead and go into topic 5.5, which is the collision theory. Let me share my screen. Okay. All right. What are we doing? We are doing, what do we just say? Elementary reactions in the collision theory. You know what? I think I'm going to do this. No, let's just go ahead. Ooh, I do not want to write with red. I don't know why. Happy Halloween. That was random. Elementary reactions. These are just single reactions, okay? We will see them applied in a little bit different way later. But what we're going to see is that this is a single step in a reaction process, okay? Is a way to kind of go ahead and start thinking about that. And these elementary reactions can be unimolecular, bimolecular, and termolecular, okay? Simple. This simply means one reactant, two reactants, three or more reactants. Okay. All right, let's look at an example. Let's say that I have X. I'm not even going to worry about what the products are because it doesn't matter. This is going to be all in terms of my reactants, okay? And if I look at this, I see that it's unimolecular, and an elementary reaction, we can write a rate law from it. Okay, so it's a single step in a whole reaction, and that'll make more sense later when we look at something called reaction mechanisms. But for right now, a reaction mechanism is a series of steps. It's how we actually get from reactants to products. An elementary reaction is one of those steps. Well, when I look at one of those steps, I can look at the stoichiometry of the reactants, and I can write the rate law from it. So remember, rate equals K, and I have one X here. So according to this elementary reaction, I don't even need to know what the products are. You would be provided with products, but it doesn't matter what they are. That would be the rate law, okay? If I had X plus X or 2X, right? That would be bimolecular. And I could write the rate from that elementary reaction, and it would be squared because I have 2X. All right. What if I had X plus Y, right? That is also bimolecular. And for this elementary reaction, the rate would equal K X Y. Okay, one more. Let's say X plus Y. Okay, this is termolecular, and the rate is equal to K, our constant. There are two X's, so that's squared Y. So all we're doing is taking our elementary reactions and writing a rate law from it by looking at the reactants and their coefficients. The coefficients turn into the orders of the reaction, okay? Cool. Next thing we're going to look at would be topic 5.5, which is your collision theory model. I honestly would have thought that this would be one of the first things that would have been brought up in kinetics, and in a traditional classroom, it's probably one of the first things I would have gone over. Collision theory. Well, this simply states that for a reaction to occur, collisions must happen. Now, there's a really key word here that I did not say, but I'm going to write. Effective collisions must occur. What needs to collide? Reactants. Okay, so for me to say collisions must occur, I don't like it. And some of y'all are going to use it, and some of you are going to hear me right now, and you're going to always write effective collisions. Effective collisions between reactants must occur, okay? Now, listen to me. Molecules can collide all day long, but if they're not effective, then no reaction is going to occur, all right? Just because they collide, just because one molecule collides with another molecule, that does not make those collisions effective, okay? What does make a collision effective? Well, collisions, in order to be effective, must have enough activation, enough energy to meet the activation energy threshold. Activation energy threshold. Okay. So when threshold, I don't know, when one element, such as, let's say, X collides with Y, or they have to collide in order to react, they must have a collision in which both particles have enough energy, all right, that matches the energy of the reaction. They need to have at least a certain amount, which will be the activation energy, or more, okay? They must also have correct orientations. All right, so I want you to think about that like this. Let's say that, I'm just gonna make this up. Let's say that X, Y, 4 plus Z yields X, Y, 3, Z plus 4. Ooh, I don't like that. I don't like that. Let me do it like this. X, Y plus Z yields X, Z plus Y. So let's draw it. I've got X, Y. I'll make him that color. And then I'm going to make him this color, okay? And then over here, I have XZ, so he's here, right? And I need the black. He's here, and he's here. Okay, so what we have here is a collision between these two particles, okay? Well, it's not going to be effective if the orange collides with the black, because then we would have an orange and a black. Right, we would see that they would maybe come together. Well, they don't come together, right? That's not what happened. So if the collision is with the orange molecule colliding with the black molecule, or the Z with the Y, that's not effective, right? This is not effective. That looks not right. There's not an effective collision. It's got the wrong orientation. Okay. Ooh, wrong orientation. Okay. Now what we would need would be to have, sorry guys, this occur, right? We would need to have, let me make that so we can see it. We would need to have Z come at it like this and collide with the white X part of the molecule. And then we would see that possibly we would end up with the molecule that we needed, and then such that the orange molecule Z would move in and be stronger attached to the white molecule X than this attraction between the black and the white molecule. I think you understand what I'm saying. And we had a collision with the correct orientation. It allowed the molecules that are going to come together to collide with each other, okay? And they also must react with the proper amount of energy, okay? Now, what is going to increase the rate of a reaction? So that's your collision theory. You've got to have effective collisions, and those effective collisions are effective if they collide with the proper enough energy and with the proper orientation. Now, what are some things that you could do to increase the likelihood that collisions will be effective? Or, right, well, how to increase likelihood of effective collisions? Well, essentially, anything you can do to cause more collisions, right? And what causes more collisions is things or particles moving around more often. And what causes particles to move around more often? Higher temperatures, lower volumes, right? They will collide more at lower volumes. Higher pressures, higher temperatures, higher surface areas allow for greater collisions. So we're looking at higher temps, right? That's going to increase the energy, right? And the number of collisions. Let's see, we could have higher concentrations, right? Because that'll lead to more collisions. And the more collisions we have, the greater likelihood we have that more of them will be effective collisions. We could have a greater surface area. That will also increase our number of collisions, right? We could have lower volumes, higher pressures. Okay, those would increase our numbers of collisions. Lower volumes, higher pressures. And once again, that would increase, we would have more collisions. So anything that could increase those number of collisions is going to increase the rate of the reaction, because it's going to increase the likelihood that you will have effective collisions, right? Keyword there is effective. Just because they're colliding doesn't mean that they're effective. Remember, they have to have enough energy and the correct orientation of molecules. Okay, and one more thing we could do, and is we could, I was just seeing that y'all weren't with me here. Okay. There's a lag. Okay, I'm gonna, because what you're seeing is not what I'm seeing. Whatever. There we go. Okay, and it real important is that we could use a catalyst. All right, use a catalyst in order to increase the rate of reaction. What do catalysts do? They increase the rate of a reaction. I'm sure you heard of them in biology, right? There's a lot of natural biological catalysts, enzymes, right? Enzymes are catalysts. What do? They lower the activation energy. All right, and you're gonna see me abbreviate that E-ACT from now on, okay? That says ACT right there. So E-ACT is for activation energy, okay? A catalyst lowers that activation energy by providing an alternate pathway. We'll look at that later. We'll look at a little bit more at catalyst later. Now let's look at an energy, kind of an energy profile, okay? And, all right. I'm waiting for my computer to catch up with me. Come on, computer. Why? I'm almost done, so don't leave me now. Right? I don't know why it is lagging. Okay, there we go. There we go. Okay, good. So down here, we're going to put good energy of molecules. And over here, we'll put number of molecules, okay? And we've seen something like this before. We know, well, we could have a curve like this, okay? And then I want you to think what's going to happen if we raise the temperature. Let me redraw that curve so I have more room. What's going to happen if we raise, oh, crud. If we raise the temperature, right? Well, we're going to flatten the curve. Remember, we're going to push the hill over towards the right and we're going to flatten it. So let's get a higher temperature here. Okay, so this will be T1, this will be T2. We know that this is the higher temperature because we've learned how to read a curve like this, right? Similar to the Maxwell-Boltzmann curve. Lower temperature. Okay, it is the Maxwell-Boltzmann curve. Well, what else can we look at this curve? There will be a line somewhere on here, okay? We'll make our line right here. Well, this is our activation energy, okay? Well, it's not our activation energy, I'm sorry. What it is that after this line, the area underneath the curve, so for the higher temperature, we've got a greater area greater number, so the area under the curve that I have highlighted represents the number of particles that have the required activation energy. The red line represents where the number of particles, there's kind of like your energy that's needed. And everybody beyond that line has the energy required. Well, at a higher temperature, we have a greater number of particles with required activation energy, right? With required activation energy. Thus, we have a greater likelihood of effective collisions. We've not only got more of them, but we've got more of them occurring with greater amounts of energy. So let me move this. Greater number of particles with required activation energy, okay? Compared to at the lower temperature, right? We only have this many number of particles. So let's just highlight that. At the lower temp, whoa, sorry, everyone. At the lower temp here, there are less particles with required activation energy. Boom. All right. There we go. I think that's good for this topic. Okay. See you guys.